Welcome to the Deep Dive, where you share your essential sources with us and we pull out the absolute core of what you need to know.
And today, we're going right back to the beginning.
We really are. We're going deep into the very foundation of chemistry. You've given us the blueprints for, well, the most basic building block of everything, the simple model of the atom.
And it sounds, elementary, but for anyone building their knowledge in chemistry, this isn't just basic. It is the bedrock.
Right.
If you're weak here, it causes these cascading mistakes later on.
Exactly. So our mission today is to quickly pull out those fundamental points and, maybe more importantly, highlight the pitfalls your sources warn about.
So you can avoid the common errors that trip people up.
Yeah, because if your understanding of the atom is shaky, then something like ionic bonding or covalent bonding.
Forget it. You'll struggle. Even just understanding the periodic table becomes much harder. Locking this down is the shortcut.
Okay, so let's unpack this. The core definition, right from your source material. The central idea is that an atom has a small, incredibly dense, positively charged nucleus.
Right, at the very center.
And it's surrounded by these much lighter, negatively charged electrons. That's the high-level view.
That's the blueprint. But to really get it, you have to appreciate the scale. The sources all describe the atom as being, well, almost empty space.
And that idea is it's genuinely mind-blowing, isn't it? Because we see these neat diagrams and they look so compact.
They're nothing like it. I mean, think of it this way, and this always helps it click for people. If the nucleus of an atom was, say, a fly, a fly sitting on the center spot of a massive football stadium, the nearest electrons would be orbiting somewhere way, way up in the highest rows of the stands.
Wow, and everything in between.
Just empty space.
Yeah.
That ratio is key to understanding why the nucleus is so significant, even though it's so tiny.
That makes it feel much more imposing. So, okay, let's nail down the physical structure based on those two locations.
Right. So you've got three key components, but only two locations.
Correct.
First, you have the center of mass, the nucleus. It's tiny, but it's incredibly dense. Almost all the mass is right there.
And inside that dense little center, you've got the two heavyweights, the protons and the neutrons.
Exactly. They're packed in there together, which gives the nucleus all that weight.
And then on the outside, you have the third particle.
The lightweight one, the electrons.
Mm.
And they're the ones moving around that nucleus in these defined pathways we call shells.
Now, I have a genuine question here. I'm trying to picture that nucleus. If protons are positive and, positive charges repel each other,
They do.
how do they all stay crammed together in that tiny space? Why doesn't it just fly apart?
That is a fantastic question, and it's where things get really fascinating. At this tiny, tiny scale, there's another force at play. It's a fundamental force of nature that's way stronger than electrical repulsion. It's called the strong nuclear force. And it basically acts like a glue, holding those protons and neutrons together and just completely overpowering their natural urge to push apart.
So there's this incredible force just to keep the foundation of matter from, well, exploding.
Pretty much, yeah. It explains the density. So now that we have location sorted, we can talk about character. Specifically, charge. This is what drives all of chemistry.
3 particles, 3 charges to master. Let's do a quick review. Protons have a positive charge.
Right, a +1 charge.
Electrons have a negative charge.
A -1.
And neutrons, just hanging out in the middle, have no charge. They are neutral.
And the essential part here is the result of all that. The atom, in its normal state, has no overall charge. It's perfectly balanced.
And that's because of that perfect 1-to-1 ratio, right? The number of positive protons has to exactly equal the number of negative electrons.
Yes, that balance is everything. And it leads us right into the mathematical definitions. This is the bit the sources flag as the cause of the most frequent error.
The identity markers, atomic number and mass number. We need to be really clear here.
Let's start with identity. If you want to know what an element is, if it's carbon or oxygen or gold, you look at its atomic number.
Okay.
The atomic number is defined as the number of protons in the nucleus, just the protons.
And that number is everything. You change the protons, you change the element.
Completely. It's non-negotiable. An atom with 6 protons is always carbon. Always. If you could somehow add one more proton, it's not carbon anymore. It's nitrogen.
It's like the element's fingerprint.
That's a perfect way to put it, yes. The atomic number is its fingerprint.
Okay, so that's identity. Now for the bulk, for the weight, the mass number.
Right. The mass number is simply the total count of the heavy particles. So that's the protons and the neutrons added together.
Because the electrons basically weigh nothing in comparison.
Their mass is negligible, yeah. So the mass number is effectively the whole mass of the atom.
And this is the part that translates into, easy marks on a test if you get it right.
It really does. Because if you know the mass number protons plus neutrons, and you know the atomic number, just protons, you can do a very simple calculation.
To find the number of neutrons.
Exactly. The number of neutrons is just the mass number minus the atomic number. It's a simple bit of subtraction, but you have to know the definitions, get them mixed up, and
you've lost the marks immediately. Okay,
Yeah.
That's a critical takeaway. So we know location, charge, and how to count everything. Now we can move to the real engine of chemistry, the electrons.
Yes, the particles that actually do all the work. We said they move in shells, but the key is understanding the rules of those shells, the capacity.
What are the limits we have to know for this model?
So the rule you have to just, have ready to go is for the first 3 shells. The first shell, the one closest to the nucleus, can only hold a maximum of 2 electrons.
Just 2, and once that's full, you move to the next one out.
You do. The second shell can hold a maximum of 8 electrons.
Okay, 2, then 8.
And for this simple model, the third shell also holds a maximum of 8 electrons. So that 2, 8, 8 configuration is your roadmap for placing electrons.
In connecting this to the bigger picture, why does that rule, that 2-8-8 rule, matter so much?
It all comes down to one word: stability. Atoms want to have a full outer shell.
Like the noble gases.
Exactly like a noble gas. A full outer shell, usually 8 electrons, makes an atom incredibly stable. Unreactive. It's happy as it is.
So an atom with, say, only 7 electrons in its outer shell is not stable. It's desperate to find one more.
Desperate is the right word. That instability is the driving force behind every chemical reaction.
Yeah.
It compels that atom to interact with others to fill that shell.
And this is the absolute crucial insight, isn't it? It's not all the electrons that are involved?
No, not at all. Only the electrons in the outermost shell, we call them the valence electrons, are actually involved in chemical reactions.
So the inner ones are just spectators.
They're passengers, yeah, tucked away safely inside. The outer shell electrons are the ones in the front line interacting with the world. Knowing that 2-8-8 rule tells you instantly which electrons are the workers.
And that one piece of knowledge underpins, well, everything. Ionic bonding, covalent bonding.
Every chemical exchange. It all comes down to those outer electrons.
That makes the structure immediately useful. It's not just a diagram to memorize. Okay, before we pull this all together, your sources had a great section on what they called knowledge tripwires.
Ah, yes. The common mistakes.
The 3 specific things to avoid saying that so you don't quite get it. We should definitely go through these.
Absolutely. This is pure tactical advice. So the first big one to avoid is saying electrons are in the nucleus.
That's a basic geographical error.
It is. Protons and neutrons are in the nucleus. Electrons are in the shells around the nucleus. 2 separate locations. You have to keep that clear.
Okay, that's number 1. What's the second tripwire?
Mixing up the atomic number and the mass number.
We talked about this. It messes up the calculation.
It does. And it shows you don't understand the difference between identity, the protons only, and mass, the protons and neutrons together.
Okay, and the third one, this one's a bit more subtle, I think.
It is, but it's about being precise. It's saying that electrons have no mass.
But they do, right? It's just very, very small.
Incredibly small. About 1/1840th the mass of a proton. So we ignore it for the mass number calculation, but to say it's 0 is just, well, it's wrong.
So the correct phrase is a very small or a negligible mass.
Exactly. Precision matters.
Excellent. Okay, we've covered structure, charges, calculations, the 2-8-8 rule, and the 3 big mistakes to avoid. Let's consolidate this into a quick self-check.
The absolute must-knows.
If you remember nothing else, remember these 3 points. Number 1, atomic number is the number of protons.
And that defines the element.
Number 2, mass number is the protons plus the neutrons.
That defines the atom's weight.
And number 3,
Electrons are in shells, and only the outer shell electrons matter for chemical reactions.
and why is getting this so right so important when you face those bigger, more complex questions?
Because those big 4 or 6 mark questions, they always require you to explain why something happens.
They demand reasoning.
Yes. If you have to explain why sodium and chlorine bond, you can't just say they stick together. You have to say, well, sodium has 1 outer electron. Its structure is 2, 8, 1.
And chlorine needs 1. Its structure is 2, 8, 7.
Right. You have to use this foundational knowledge to build your answer. Without it, you can't explain anything properly.
So what does this mastery really mean for you, for the listener? How does it empower you?
It's a huge shortcut. It means you understand the entire architecture of the periodic table. The columns, the groups, they aren't random. They're arranged by the number of outer shell electrons.
So everything in group 1 has one outer electron. Everything in group 17 has 7.
Precisely. So if you know an element's atomic number, you can use the 288 rule to place it. You can immediately predict its personality.
You can predict if it wants to lose electrons or gain them or share them.
You move from just memorizing that, say, sodium is reactive,
Yeah.
to understanding mechanically why it's reactive.
Yeah.
Because it's desperate to get rid of that one lonely outer electron to get a stable, full shell underneath.
And that kind of deep structural thinking, that's the whole goal of this deep dive.
It really is. It takes you from just describing chemistry to actually understanding why it all happens. It saves you so much time later on.
And that's the payoff. Well,
Yeah.
thank you for sharing these sources with us and letting us walk you through the anatomy of the atom.
It was a pleasure.
Yeah.
But, before we go, let's circle back to that idea of neutrality. We spent a lot of time on the fact that an atom is balanced.
Right. The protons and electrons are in a perfect equilibrium.
The natural state of things, yes.
Yeah. But what happens if you deliberately break that balance? We talked about atoms wanting to gain or lose electrons to get stable.
When an atom does that, it shatters that perfect positive-negative equality. So think about what that means. What new kind of thing is created when that fundamental balance is broken? What new property does it have? That's the next step for you to explore.
A fantastic question to lead us into the world of chemical interactions. We'll catch you next time for the next deep dive.